In this video we want to have a look at entropy. Now entropy can be defined as it's the measure of the disorder of a system or the randomness of a system. It is given the symbol S. A highly ordered system will have low entropy, where a very disordered system will have high entropy. And that's kind of what this little image is showing you here. You've got a highly ordered system here, which is going to have a low entropy. If this thing here breaks up into individual pieces, there'll be more disorder in those individual pieces there. So that's going to have a high entropy. So there's an increase in entropy going from this ordered system to this more disordered system. Now, how you can work these things out? If we look at state changes to start off with. So entropy changes with a state change. So as you can see here on this graph, on the y-axis here we've got the entropy, and at the bottom here on the x we've got temperature. And we're looking at here, there's divisions here for melting points and boiling points here. So you've got solids, liquids going to gases here. So solids are more ordered, so they have less entropy, hence this is why it's lower down on the graph here. Whereas gases are more disordered, they move randomly, so they'll have greater entropy. This is why you've got your line up here on this graph. So you can see here, going from a H2O solid to liquid and then maybe gas, you're going to get an increase in entropy, and that's because liquid particles and gas particles have the freedom to move, more random movements, more disorder, more entropy. Another way is looking at temperature. When temperature increases, the particles will have more kinetic energy, so they're moving faster and randomly, so therefore entropy would increase. So if you're thinking about endothermic and exothermic reactions, if you remember, endothermic reactions absorb heat from the surroundings, exothermic reactions release heat to the surroundings. So if you've got an exothermic reaction that's releasing heat and energy to surroundings, it means all those air particles in the surroundings are going to gain that energy. They're going to be moving faster, moving more randomly. There's going to be an increase in entropy. So if we have a look at that, exothermic reactions have an increase in entropy, endothermic reactions have a decrease in entropy. Another way of being able to measure this is the number of moles. As the number of moles increase, so does the entropy. Think about it logically. If you've got more particles present, there's more chance that those particles can be in different locations, different vibrations. This means there's going to be a difference in randomness, disorder, so therefore it's going to be an increase in entropy. So if we have a look at this reaction here, the Haber process, nitrogen plus hydrogen to give you ammonia. On the reactant side, you've got 4 moles of particles, whereas on the product side, you've got 2 moles. There's going to be more disorder in 4 moles than 2 moles, so as the reaction goes from the ammonia, the hydrogen to the nitrogen, the hydrogen to the ammonia, you can say that there's a decrease in entropy there. Dissolving. When you put a substance in water, or you dissolve a substance, the entropy is going to increase as aqueous ions are more disordered than the solid. So an example here is sodium chloride. If you put some sodium chloride into some water, that sodium chloride is going to break apart into the sodium ion and the chloride ion. There's more disorder in ions that are free to move, so there's an increase in entropy from dissolving. Now, when we're discussing these, you'd be expected to be able to discuss the system and the surroundings. Now, what the system is, it's the reaction you're talking about. So, for instance, magnesium plus oxygen to give you magnesium oxide there. That's a system, it's the reaction. The surroundings is everything else, and it's defined as the universe. So e.g., it's the air, it's the beaker, it's the desk, it's your hand if you're holding the beaker or the test tube. Basically, the surroundings is everything else, that's not that particular reaction. Another thing you'd have to be aware of is spontaneous and non-spontaneous. Now, a reaction is spontaneous if it occurs without any help. So e.g., you don't have to heat it up, so you're not getting the Bunsen burner out to heat it up. A non-spontaneous reaction can happen, but it needs energy to occur. So those are the reactions that we are heating up and getting the Bunsen burner out and things for, okay, because they're non-spontaneous. They don't happen by themselves. So when we're trying to work out whether a reaction overall is going to occur, whether it's spontaneous or not, what we have to look at is when we put the entropy of the system and add that to the entropy of the surroundings, if we end up with a positive overall in entropy, then that means our reaction is spontaneous. If we add up the system entropy and the surroundings entropy, and we end up with a negative, that means it's not going to be spontaneous. So what we're looking at, remember S stands for entropy, so the system plus the surroundings, whether it's positive or negative. If it's positive, it's spontaneous. If it's negative, it's not spontaneous. Look at an example here. So we've got N2H4 plus O2 gives us N2 plus 2H2O. Our entropy for that is minus 624 kilojoules per mole. So remember, when we're talking about the system, we're talking about the reaction itself. So the reaction itself is your N2H4 plus oxygen producing your N2 plus 2H2O. And this is where you're looking at what state they're in and how many moles are present. So you can see here, all of them are gases, and then you can add up the moles on both sides. So on the reactant side, you've got 2 moles of gas because you've got 1 N2H4 and 1 O2. On the product side, you've got 3 moles of gas because you've got 1 lot of nitrogen and 2 lots of water there. So you're going from 2 moles to 3 moles. So for the system, there'll be an increase in entropy because there's more randomness in 3 moles of gas than there is in 2 moles of gas. When we're looking at the surroundings, what we're looking at here is the entropy change. Now, the entropy change here is a negative change. So that means that the reaction is exothermic. So we're looking at what's happening to the surroundings. Remember, exothermic reactions release heat energy to the surroundings. So the air particles in the surroundings are going to gain that energy. They're going to be moving faster, more randomly. So the surroundings are going to have an increase in entropy. So if you have a look at overall, the system had an increase in entropy because you were going from 2 moles to 3 moles. The surroundings had an increase in entropy because you had a negative entropy there because it was exothermic. So overall, there's an increase in entropy for both of them. So you're going to end up with a positive in entropy. So the reaction's going to be spontaneous. It's going to be a spontaneous reaction there. Looking at another one here. Sodium chloride is going to dissolve into the sodium ion and the chloride ion. The entropy of this reaction is positive 3.90 kilojoules per mole. So again, we're looking at system and we're looking at surroundings. So if we have a look at the system to start with, so the system is your sodium chloride dissolving into its ions. So here you are going to be looking at the states that they're in and the number of moles that you have. So first off, our sodium chloride is solid. Solids are very ordered, so that's got a low entropy, whereas it's dissolving into the sodium ion and the chloride ion. They're ions, they're free to move, so they have more randomness, more disorder. So there's an increase in entropy or greater entropy in the products there, in the sodium and the chloride ions. Also, if you look at the moles, you're starting off with 1 mole and you're going to 2 moles. So that also is an increase in entropy there. So for the system, you have an increase in entropy, a positive in entropy there. Now remember, when we talk about the surroundings, what we're talking about here is our entropy for the reaction, for surroundings. Now in this case here, our entropy here is positive because it's an endothermic reaction there, which means the surroundings are going to be losing energy. So if the particles in the surroundings are losing energy, that means they're slowing down and they're going to become less random and more ordered. So in endothermic reactions, you're going to get a decrease in entropy. So that leaves you with a situation here saying, well, when we put systems plus surroundings, we don't know which one's greater. Is it greater entropy in the system than the surroundings? Are we going to end up with a positive number or a negative number at the end? We don't know. And this is why in the exam, the question will tell you whether it's spontaneous or not. So the question will say, explain why this is spontaneous, or explain why this occurs, or explain why you see this substance dissolve in water. So that question's telling you whether it's spontaneous or not. So for example here, the 2019 exam says, justify in terms of the entropy changes of the system and surroundings why the reaction is spontaneous. So it's telling you it's spontaneous in the exam question there.